All right, I'm going to recap what we learned today in class by first showing you how to generate a shorthand electron configuration for the element niobium. Here's the element niobium. To shortcut niobium, we're going to look to the noble gas on the row that precedes niobium, which is krypton. We're going to put krypton in brackets, and then we're going to configure the row that niobium is a part of from the beginning of the row up to and including each sublevel section until we get to niobium. At the beginning of this row is the energy level 5. The first sublevel we come to is S. Niobium is not part of the 5s, so it takes 2 electrons to fill. Now we're going to move into the D sublevel section. Notice on your periodic table map, I had you note that the D sublevel here is going to be labeled 4D. In general, the energy associated with Ds is one less than the true row number. And you'll just kind of have to remember that. That's one of the reasons why I put it on your map. So we are at 4D. To get to niobium, you count in 1, 2, 3 squares. So that is the formal electron configuration in shorthand for niobium. Now what I want to do is I want to take this shorthand electron configuration and I want to change it to an orbital notation. The orbital notation is going to have all the same information. It's going to keep the symbol of krypton in brackets. It's going to keep the energy level and sublevel letters. But instead of just doing a total of electrons, I'm going to draw a picture of something called an atomic orbital. And the shape of that picture doesn't really matter. For our purposes, I'm going to use a circle. Instead of using a total number of electrons, I'm going to represent my electrons with a symbol. So I'm going to use a little slash to represent my electrons. So if I want to transform my electron configuration into an orbital notation, I'm going to bring down my shortcut symbol in brackets. I'm going to bring down the 5 and the S, and then I'm going to consult my periodic table to see how many orbitals I'm supposed to draw with an S. If you look at your periodic table, the energy sublevel S has 1 orbital associated with it. So I'm going to draw 1 orbital. Now, within that orbital, I'm supposed to put 2 electrons. The Pauli exclusionary rule says this orbital can contain 2 electrons, but you have to show them as going in opposite directions. So I'm going to draw 1 electron going this direction and 1 electron going that direction. I'm then going to bring down 4 and D, and then I'm going to look, my periodic table says you draw 5 orbitals for Ds. So I'm going to draw 1, 2, 3, 4, 5 for the D. And then I'm going to distribute those 3 electrons into the d orbitals. I'm going to make sure that I follow Hund's rule. Hund's rule says I should place 1 electron per orbital, sharing them out before I do any pairing up. So 1, 2, 3. Now, I want you to notice that these 2 orbitals are empty. That's okay. You should still draw the empty orbitals, okay, because that is important. One of my favorite follow-up questions to this, which kind of goes along with question 3 on your initial homework, is once you draw the orbital notation, tell me how many unpaired electrons are in the picture. If you disregard the empty orbitals, look at only the orbitals that have a single electron. There are 1, 2, 3 unpaired electrons. So niobium has 3 unpaired electrons. I hope this was a decent follow-up to what we looked at in class today.